This video will talk about cell potential and how we measure it relative to the standard conditions. First of all, a cell potential refers to how likely or how energetically a reaction is going to happen compared to something else. Overall, our cell potential equation is given by the formula: the cell potential of the cathode or our oxidizing agent minus the cell potential of our anode, our reducing agent. Now notice that these are all reduction potentials, noted by the little r, and these are all the values found in your Chemistry 30 data booklet on page 7. Sometimes some other textbooks use what's called the oxidation potential, and you'll notice that by the use of little o. We don't use this in Chem 30, but you should be aware of it, that it's out there. If the net difference between the reduction potential of the cathode minus the anode is positive, then we'll have a spontaneous voltaic reaction. If, however, the difference gives a negative value, this is a non-spontaneous or electrolytic reaction, which we'll talk about in a future video. To state another way, if the cell potential is positive, that means there's enough what's called electromotive force, enough potential difference for the electrons to move from the reduction agent that's being oxidized to the oxidation agent, which is being reduced. Now, all of the values found on page 7 of the Chemistry 30 data booklet are measured under standard cell conditions, which means that they are measured under SATP, standard ambient temperature and pressure, so 25 degrees and 100 kilopascal, and a concentration of 1 mole per liter for all aqueous solutions. So for example, in a zinc dichromate cell, the concentration of zinc ion is 1 mole per liter, as well as the dichromate ions, and the hydronium ions, as well as the chromium 3 ions. And once again, the conditions are SATP, standard ambient temperature and pressure. So the standard cell potential is the maximum electrical potential difference, or in other words, the voltage, of a certain cell under standard conditions at SATP and 1 mole per liter concentration of aqueous solutions. This is only the maximum difference, between the cathode and the anode. Important to note that the bigger positive cell potential values means that the reactants, the oxidizing agent, are more likely to attract the electrons. Now, when we talk about these potential values, we have to measure them against something. Therefore, scientists have arbitrarily determined that the standard hydrogen half cell, that is 1 mole per liter of hydrogen ions and 1 atmosphere of pressure for hydrogen gas, is the standard cell that we measure everything to. So all the reducing strength in the reduction half table are measured relative to the standard hydrogen half cell. Let's take a closer look at the standard hydrogen half cell. We have a solution of hydrochloric acid or hydrogen ions being reduced with electrons at an inert electrode to produce hydrogen gas. And this has a arbitrarily defined cell potential of 0 volts. You'll also note that the concentration of hydrogen ions is 1 mole per liter at 25 degrees, and the hydrogen is at 101 kilopascal. Now, all the cell potentials recorded in your Chemistry 30 data booklet are recorded with respect to the hydrogen half cell. However, scientists could have easily picked a different half cell, but then all of the values in the cell potential would change. So for example, if scientists had used the reduction of silver ions into solid silver, right now our cell potential as read from the chemistry data booklet is positive 0.80 volts. If scientists had used this way as the standard potential, so let's say E is 0, then the potential of the hydrogen half cell would now be negative 0.80 volts, because every value in the cell potential data table would have to be changed by 0.8 volts. Let's look at a specific example where we connect the copper half cell against the standard hydrogen half cell. If we connect it to a voltmeter, we see that the voltage will be positive 0.34 volts. That means that the reduction of copper ion into copper solid is more likely to happen, more likely to gain electron compared to hydrogen ions. Therefore, we know that it's going to be a stronger oxidizing agent than hydrogen ions. It is more likely to be reduced than hydrogen ions. If we look at another example, this time the half cell between zinc ion against the standard hydrogen ions, our voltmeter tells us it's negative 0.76 volts, which means that the zinc is unlikely to be reduced compared to the hydrogen ions. It is more likely to lose electrons than hydrogen gas. So then zinc is what's called a stronger reducing agent, more likely to be oxidized than our hydrogen gas. And remember, this oxidation of hydrogen gas is going to happen at an inert electrode because there's no such thing as a solid piece of hydrogen that we can use as an electrode. So in your textbook as well as your data booklet, all the cell potential written are for the reduction reactions. You have, example in this case, fluorine gas being reduced into fluoride ions. That is the strongest oxidation, that is the most energetic reduction reaction measured by our table at a cell potential of 2.87 volts. So this table is for standard reduction potential. However, if we're to determine the oxidation potential, we'll need to write the equation in reverse. And when the equation is written in reverse, the sign of the cell potential changes from positive to negative or from negative to positive. So for example, in the oxidation of fluoride ion to fluorine gas, the cell potential would be negative 2.87 volts. However, when we change the stoichiometric ratios, the stoichiometric coefficient, we do not change the value of the standard cell potential. Let's now predict the overall cell potential for any given reaction. So in our example here, we have zinc and copper half cells, and we find that our zinc solid is going to be our strongest reducing agent, which will be oxidized at our anode. And we will have our copper ion, which is our strongest oxidizing agent. It will be reduced at the cathode. Now remember, our table of values in our data booklet and our textbook are reduction potential. Therefore, we can simply read those values for the reduction of the strongest oxidation agent at the cathode. And the value there in the table is positive 0.34 volts. On the other hand, if we have to find the oxidation potential of our anode, our strongest reducing agent, we have to take the negative value of that. In our data booklet, the value is negative 0.76. However, the negative of a negative is positive 0.76. So the oxidation potential for our zinc reaction is positive 0.76. When we add those two equations together, our oxidation half reaction and our reduction half reaction, the overall cell potential is positive 1.10 volts. And remember, a positive cell potential means this is going to be a spontaneous reaction in a voltaic cell. An alternative way to determine the cell potential is to use the formula cell potential is the reduction potential of the cathode minus, that's the key, minus the reduction potential at the anode. Of course, in order to do that, you must first determine what is the strongest reducing agent, or the anode, this oxidizing agent at the cathode. Once we've determined that, we can take the values from our data table and simply take the cell potential of our cathode minus the cell potential of the anode. In this case, our net cell potential is positive 1.10 volts, which is the same as our previous slide. Now remember, all the values reported in the table are under standard conditions. Therefore, non-standard conditions, so conditions not at SATP or not 1 mole per liter concentration, will cause a different cell potential. This is because this is causing a shift in the equilibrium either towards the product of our reduction reaction or towards the reactants in our reduction half reactions. For example, if we're to look at the reduction of copper ion into copper solid, if we're to add more aqueous reactants, or in this case copper ions, we would shift the reaction towards the products, causing the cell potential to increase. However, what if we're to add more copper solid? Now remember, copper solid, being a solid compound, does not have a concentration, and therefore if we're to add more solid copper into a reaction, we would not shift the equation back towards the reactants. Now usually these shifts in equations in cell potential are generally small if the differences is relatively close to the standard values. In Chemistry 30, all measurements are recorded with respect to standard conditions, and you will not be expected to know non-standard conditions. Other discrepancies that could cause a reaction to differ from the standard cell potential are the purity of the substances, such as an oxide or a rust coating, and the type and the boundary size of the porous material in your salt bridge. These are both experimental errors which you cannot control for in a standard high school laboratory.